Still in 8.2, now we're doing example 4. And this is the repeated use of integration by parts, kind of like what we were talking about a few minutes ago, but in this case, this is the reason you can't use the tabular method. No matter which one of these you pick as your u, you cannot take derivatives down to 0. It's never going to go to 0. They just keep going. So what you do is you pick your u and your dv for your first shot. When you pick the second shot at it, you have to use the same thing. If I use the e in the u spot and the trig function in the dv spot, I have to do the same method. Pick it the same way, because then something interesting will happen. It will take you 2 shots around before you see it happen. So we're going to write, I'm going to pick the u to be the e to the 2x and the dv to be the sine of x. Now, the problem, can I pick it the other way? Yes, you can pick it the other way. It will still work. But integrating e to the 2x is going to cause you to have to keep sticking a 1/2 in front of it, because its derivative needs to cancel out that 2 that you're going to put out there. So it's easier to take derivatives of stuff like that than it is to integrate them. So I always pick the harder one as my derivative. So du is going to be e to the 2x times the 2. There's that 2 I was talking about. And v, the integral of the sine, would be negative cosine. So when you're doing one of these problems that never ends like this, you have to rewrite the question every single time on the left-hand side of the equal sign, because we get lazy and we just keep putting equal signs. But you're not going to see the pattern happen unless you keep writing that first piece out. So I'm going to write it every time. My rule says uv, so negative e to the 2x cosine of x minus the integral of v du. That's going to be negative 2 e to the 2x cosine of x dx. I got a little close there. Okay, so now rewrite the first piece. Don't lose it. I'm going to clean this up a little bit. Make that a plus, pull the 2 on the outside. And now we're going to try the technique again, and got to do the same thing. So you're going to pick your u to be the e function and your dv to be the trig function. Its integral would be sine, and this guy's derivative would be 2 e to the x dx. So now, starting by rewriting the original question, I know it's a pain, but if you don't, you're not going to see this. I have a negative e to the 2x cosine of x plus a 2 bracket. So this integral is going to become uv minus the integral of v du, close the brackets, rewrite it again, and that's going to give me negative e to the negative 2x cosine of x. I'm going to distribute that 2. I'm going to pull the 2 out of the integral with the 2 that I'm distributing, so 4. So now I have this. Okay, now take a look at this. This integral that we have left, that you're looking at going, man, it's just going to keep chasing my tail. I'm never going to finish. It is identical to the problem over here. So what I'm going to do is there are negative 4 of them on the right side. I'm going to add 4 of them to the left side. Oops, I lost a 2, didn't I? I did, right here. Oh, because I didn't write it right there. Let me fix this. Okay. Now when I put these together, I not only have the 1, I also have 4 more, so I have 5 of them. And then I have this over here still left. And now all I have to do to get the answer is divide all the way through by a 5. If I divide through by a 5, I get the integral of e to the 2x sine of x dx, which if you look, that was the original question, so I am solving the original question, equals, now what can I pull out of this nonsense? I can pull out a 1/5 and an e to the negative 2x, and if I turn the binomial around so that I have the negative in the middle, I will have 2, took the e to the 2x out, sine of x minus the cosine of x left here, and then don't forget your plus c. So that's how you, why did I write a negative? Oh my goodness. I'm just making negative signs for no apparent reason. There we go. All fixed. Okay, so now if you look at it, you actually have the final answer to the question because you kept bringing down the left-hand side. If you don't bring it down, you're not going to notice, and I've had people go through UDV like 3, 4, 5 times, and they keep saying it's never going to end, and I keep saying, yes, what's wrong with it? So if you don't bring it down, you're not going to see what to do. So be careful with that. Now we're going to do example 5, and example 5 is just doing a definite integral, and it's exactly the same thing. It's just that when you're totally finished with the problem, you have to do the plug and chug for the numbers that they gave you. So here's the question. Now this one's interesting because you don't really see 2 parts to it. But here's the thing. You only know how to take the derivative of the natural log of x. You don't know how to integrate the natural log of x. There were no rules for that. So immediately your u should be designated as the natural log of x. So what is left for your dv? Just the dx. Integrate dx and you get 1. Take the derivative of the natural log of x and you get 1 over x dx. So using my formula, uv, so that's 1 times the natural log of x, uv, oh no, that's an x. Well then, sorry. It's integrating 1 and you get x. So you get x the natural log of x minus the integral of v du, and oh, this is interesting. So that's x the natural log of x minus the integral of dx, which is just x. But then don't forget, you were supposed to be evaluating it. So what should be happening, and I didn't do it this way because the same thing's going to happen to you, you get caught up in the problem. But when you do the uv, you should have your 1 to 2 right there. When you write the v du, you should have the 1 to 2 right there. And now it's a plug and chug. So now that's going to be 2 the natural log of 2 minus 2, subtract 1 the natural log of 1 minus 1. Natural log of 1 is 0, so you get a plus 1 on the end. So you get 2 the natural log of 2 minus 1. And if you wanted a decimal version for that, you'd go to your calculator and put it in and get 0.386. All right, number 6. And at this point, since we've integrated number 5, that actually gives you a rule. That rule, let me move this out of the way, is now, and you can memorize this and it will save you time, the integral of the natural log of x is x the natural log of x minus x plus the constant. So we've actually just derived a new integral that we should probably memorize. Okay, example 6 is going back to the solids of revolution that we were doing before. We did them in Calc 1. And it says, let R be the region bounded by y equals the natural log of x, the x-axis, and the line x equals a, where a is greater than 1. Find the volume of the solid that is generated when the region R is revolved around the x-axis. Okay, so revolved around the x-axis. If you graphed the natural log of x, here's 1, it would look like this. And now you want to go from x equals a, okay, x-axis, x equals a. Did I read that right, x-axis? Yes. So we're going to, here's A, some point where A is greater than 1. So we're looking for this region right here, and we're revolving it around the x-axis. So if I take my representative rectangle, and I say, oh, it's a thickness of dx, so my rectangle is in x's, and if I'm flipping it around the x-axis, I'm making a circle, and the area of a circle is pi r squared. So we're doing, this is the washer method or disk method, which means circles. So pi r squared, well, r is that function. The radius is this height. This is r. So my function is going to be put right here, ln of x quantity squared. So we are integrating from 1 to a, this is my volume I'm looking for, of pi ln of x squared dx. Okay, so now we're going to, I'm going to pull the pi out, I don't need that there. 1 to a of the natural log of x squared dx. So what do we pick for u? I'm going to pick the u to be the natural log of x, because again, that's the one I know the derivative of. And then the dv would be the dx, which means that v came from x, and du came from 1 over x dx. So substitution. That would be u squared oh, wait a minute. That's not what I meant to write. Pi times the whole nonsense, and so that's going to be uv back up. I forgot the square. Got to put it in here. So this derivative is not right. This derivative would be 2, the natural log of x, times the derivative of x. Okay, so uv, which would be x, the natural log of x squared, minus the integral of v du, which gives me 2 in x and ln of x of 1 over x dx. I need to change the variables on this, or I can put them back when I'm done. I think I'll just put them back when I'm done. It'll work fine. So I have a pi x, the natural log of x squared, minus, let's clean this up. I can pull the 2 out. The x and the 1 over x cancel, so now I have ln of x dx. Oh, but we just finished doing that one. We know its answer, so this is x, the natural log of x squared, minus 2, parentheses, what's the integral of the natural log of x? It is x, natural log of x, minus x, from the previous example. And then close the brackets. So now I'm evaluating this from 1 to a. Again, notice I left off the evaluations. That's fine. As long as you stick them back in at the end, you're good. So I'm going to get a pi on the outside, a natural log of a squared minus 2. I'm going to distribute the 2. 2a natural log of a minus a. And then I have to, minus 2a. And then I have to subtract, plugging in 1. 1, the natural log of 1 squared minus 2 times natural log of 1, natural log of 1 minus 1. Too many parentheses. Bracket. Okay, let's see what I've got left here. I've got a pi on the outside. Natural log of 1 is 0, so that's gone. Natural log of 1 is 0, so that's gone. So I have my a natural log of a squared, my minus 2a natural log of a, my why do I have a minus here? Oh yeah, this should be a plus. Somewhere I lost it. It's a plus 2a. This should be the minus 2. That should be a plus. So I get a plus 2a, and then I have The negative 2 times the negative 1 in parentheses is 2, with the negative in front is a minus 2. Close it. It looks really ugly, but that's the way it's going to be because we're using a. They didn't give us a number to work with. And this question would have been much easier if they had given us 1 to some other number. This concludes 8.2.